All right, so far, most of what we've looked at have been problems that have polynomial time algorithms, right? And in most cases that we've looked at things that have actually very small exponents in the polynomial. We've looked at mostly things that in the worst case have been quadratic or maybe a quadratic times something. So we haven't seen any of the hard problems yet. Okay, well actually we did. We have seen a couple, but we haven't really gone into detail. All right, so the idea is that some problems, the ones that we've been looking at, are big O of n to the k for some constant k. There are some problems that can't be solved by a computer at all. We haven't really talked about any of those, but there are some things that we can't solve at all. But there are others that we've kind of hinted at, the TSP, for example, trying to find the minimum cost cycle that goes through every vertex exactly once. We haven't seen a good algorithm yet. We saw a fast algorithm. We saw the nearest neighbor algorithm. Just go from wherever you are to whatever's closest to whatever's closest until you get back to the beginning, the closest place you haven't been to. It was fast, but it didn't give good answers. Right? In some of the assigned problems, it actually gave the worst answer possible. And so we've seen fast but not correct. We've seen correct but definitely not fast, right? The brute force approach of looking at every single path or every single cycle, checking all of the cycles, and that wasn't good. And these only worked in a complete graph anyway, so these only worked if all the possible connections were there. And so so that nearest neighbor thing could sometimes use up all the edges so that you couldn't even get back to the starting point. So so we want to try to organize this idea a little bit. So when we talk about polynomial time algorithms, we might have something that is like big O of n to the 100th power or something, right? That's polynomial time, which in any kind of real-life scenario, not even a real-life scenario, really small values of n, this would be an incredibly long amount of time to try to solve a particular problem. So if you had something that was big O of n to the 100th, that wouldn't actually be an easy computational problem. It would still take a lot of time to try to solve that in those worst cases. But usually what happens when someone discovers an algorithm that is polynomial, then really quickly somebody discovers one that's faster and faster to whatever the fastest possibility is. So usually once something is found to be polynomial, even if it's a really big exponent like that, pretty quickly that exponent gets reduced way down. Now, not always, but usually that's what happens. So what we're going to think of with polynomial time is we're going to think of these as being the easy problems, or what we say tractable. That means things that you can expect to be able to compute the answer to. So again, there might be situations where you can't really because the exponent, even if it's polynomial, might be too big for certain situations. But usually that resolves over a rather short amount of time. Things that are super polynomial, so bigger than any polynomial, which might be factorial, which might be exponential, These are the hard problems. These are the ones that we say are intractable. Now there's a difference here. Up until now, we've been talking about an algorithm being polynomial or superpolynomial. We're talking now about the problem itself. All right, so we're going to look at the problem, and we're going to be able to say, rather than this algorithm is polynomial time, we're going to say that this problem is solvable in this time, or at this point is unknown to be solvable, or cannot be solved in polynomial time, and so on. So what we're saying, if we say a problem is polynomial, if this is not being very careful, but if we say this kind of thing, this particular problem is polynomial, what that means is that it can be solved in polynomial time. All right, so it's kind of that saying a problem is polynomial really means that it can be solved in polynomial time. So that means that there's at least one algorithm that solves that problem in polynomial time. Again, polynomial time in terms of the input, how we're measuring the size of the input has an effect in all this. There's a lot of technical details that we would need to get into if we were going to be proving a lot of real things about this, but we want the conceptual approach right now. So when we talk about a problem being able to be solved in polynomial time, we will then often just say, yes, that problem is, the problem is polynomial. It's not actually quite correct. Okay, so what happens? We have several problems that we know about that are in this category. So the tractable kinds of problems. A tractable kind of problem, for instance, is sorting. Right? We know that we have lots of algorithms for sorting. Some are faster than others, but even most of the bad algorithms that we know for sorting are still polynomial time. There are some that are worse. What's the worst sorting algorithm you know of? Random sort, right? Random sort just says, okay, let's take everything, throw them all up in the air, let them fall, check to see if they're in order. If they're not, pick them all up and throw them again. What will happen eventually? Eventually they'll fall in order, right? I mean, there's a non-zero probability that they'll fall in order. That's going to take a while, right? Especially if there are more and more things. All right, so let's improve on that algorithm just a little bit. Let's pick them all up and throw them. When they land, we check to see, okay, these are in order, these first few are in order, and then after that they're not, so let's just shuffle those again. Will that work? A little faster? All right, so what if our numbers that we were sorting in that approach were 1 through 100? And so we're going to, we shuffle them, check to see are they in order. The ones that are in order, we keep those fixed, and we just shuffle the rest of them. What if our first three numbers were 97, 98, and 99, and then everything else? If we kept those in place and shuffled these, what would happen? They would never be in order, would they? So that algorithm won't work the way that some of the others did, where we could say, okay, well, this part's already in order. It's not broken. Let's keep it and work with the other part. This random shuffling thing wouldn't work in that case, right? So what would we have to do? This would actually give us an algorithm that almost certainly wouldn't work. Because sometimes you're going to have some numbers that are okay at the beginning, but they're not where they need to be overall. And so we can't always even take a bad algorithm and try to improve on it, because sometimes trying to improve on a bad algorithm makes it even worse, right? So will random sort eventually get you the right answer? Yes, but if we try to tweak it, at least in that way, it's not even guaranteed anymore to eventually give us the right answer. It might always give the wrong answer. Okay, so sorting, though, is tractable because there are lots of other methods that we've seen to be able to sort in a quick way. So tractable problems that are, again, on this side. So I'm going to match up some things. Sorting, I don't have anything to match on the intractable side. But we've spent some time now looking at shortest path. Shortest path between two vertices, or shortest path between all possible pairs. And so we know that those algorithms are polynomial in terms of either the size or the order of a graph, or possibly some combination of both pieces being involved. A corresponding problem to shortest path that we've mentioned briefly that has something different about it. Shortest path is easy. Longest simple path is not. Or at least if it is, nobody knows how to solve it. But so simple path is, we talked about last time, one that doesn't ever revisit any vertex or use the same edge again. Right? So it never revisits any particular vertex. Or since it can't revisit a vertex, it can't reuse an edge. All right. We don't have to say that on shortest path. We don't have to say simple, because if you're reusing an edge, then you could have just not reused it and been shorter. Okay. We also talked about, when we were talking about the bridges problem, we talked about an Euler-Tour, where you want to use all of the edges exactly once, but you're allowed to revisit vertices. And we know how to check to see if there is an Euler-Tour. What do we do to see if there's an Euler-Tour that starts and ends at the same place? We would count the degrees, check the degrees of each vertex. If there are any odd degrees, there's no Euler-Tour. If they are all even and the graph is connected, then there's an Euler-Tour. Not only can you check to see if there's a tour, you can find such a tour. And both of these approaches are big O of whatever the size of the graph is. So the Euler-Tour problem, is there a tour? Find one if it exists. These are both pretty easy problems. Change this to visit each vertex exactly once. And that's the Hamilton or Hamiltonian cycle problem. And that problem is lots harder. Even telling whether there is a Hamiltonian cycle in a graph becomes much more difficult. We're going to see a problem today that is about Boolean operations, or about Boolean expressions that we're checking to see if they're true or false. We're trying to assign values to see if something is true or false. So this CNF means conjunctive normal form. And so this has to do with with Boolean expressions where we're using ands and ors. All right, so what we look at with conjunctive normal form is we have some clauses, or you have variables in there. And these are just Booleans, right? So we have maybe x1. They're joined inside the clauses with or. So maybe we have x1 or the negation of x2. And then the clauses themselves are joined by ands. Remember, we use those notation for or and and. I guess we could just write it out. Maybe if this will erase. These are ors. These are ands. And we can have maybe x2 or x3, and we can keep going on and on like this. So the to part in this means that inside each clause, there are always two of our variables. The C and F part, the conjunctive normal form, means that inside the parentheses it's always or, and between parentheses is always and. And this part stands for satisfiability. Is trying to find true or false values for x1, x2, and in this case x3 that will make the whole thing true. All right, so let's see in this small example, what should we make x1 be? We need to assign values for x1, x2, and x3. We want the whole thing to be true. So what could we do? We could make x1 be, we could make it true. x2, we could make false if we like. If we make x2 false, what do we have to make x3? x3 would have to be true. So what happens? This clause is true because x1 is true. This clause is true because x2 is true, x3 is true. And so the whole thing is true and true is a true statement. Is this the only solution to this particular thing? No. We could have made x1 be false. And what would have happened? Keep these the same. This is still true, so this clause is true. And x3 is still true, so that's still true. So there's more than one solution, possibly, in some cases. All right, but the idea of 2C and F sat is we might have lots and lots and lots of clauses. They're all ors inside parentheses and ands in between. And there might be how many different variables you want. But what happens, it turns out that we can always solve this problem pretty quickly. Right? That we can always figure out evaluations for the variables to make the whole thing true. Now, we're not going to get into the details right now of how what that algorithm would look like. You get to do that on your own. All right, so this problem, easy. Turns out that if we change the 2 to a 3, which means we have sets of 3 values in all of the clauses, that this problem is not easy. Yes?
What's the SAT stand?
Satisfiability. So that was the little bit that I had written over here. Satisfiability means we're trying to find the values, the Boolean values for each of the variables that will satisfy the expression and make the whole thing true. Or determine that there are no such ways to, right? If I do something like this, well, could there be some situation is there some way of creating an expression that doesn't have any way at all of assigning the truth values? If that were to happen, then your algorithm would need to say that as well. It's like, no, this can never be true. This thing is always false. The difference between 2SAT, or 2C and F sat, and 3C and F sat is in terms of the just the number of terms. You add the one extra term in every set of parentheses, and suddenly the problem becomes very, very difficult to solve. Okay, so we're going to take a look at this idea in a little more abstract setting. All right, we have what we're getting ready to talk about isn't really in terms of solving the problems the way we've been solving them before. We've been solving the problems before that have involved like find a shortest path or find a smallest cycle or calculate something in this way. And so these are what are called optimization problems. We've talked about optimization. The optimization problems are trying to find the actual value. What we're actually looking at now are what are called decision problems. And a decision problem is a yes or no question. But you might ask it like this. If we wanted a shortest path, so we might be given a graph G So the way this is often written, instead of saying given, we say an instance of the problem is a graph G and a positive integer k. And then the question, which is a yes or no question, actually, shortest path, you would need the graph G, positive integer k, and maybe your two vertices, the two ends of the path. All right, so we get something that looks like this. Is there a path between A and B whose weight is less than or equal to k? So we don't get the minimization problem or the actual optimization problem. We get a yes or no question. All right, so what we're talking about is actually in terms of yes or no questions. The Hamiltonian cycle problem. Well, so you're given the k when you start.
Oh, okay.
Right? So you have your graph, you have your vertices, you have your k.
So you actually have all the information.
And so, yeah, so that's what instance. We're given that information, okay, and then we're just trying to answer the question. Now, what could you do? If we could solve this problem quickly, we could just keep changing k and solve the problem again and again and again until we found that there is a path of this length and not one of the next smaller k, or not one for any k that's smaller than that. Right? So we could use it to solve the optimization problem by kind of repeating the process over and over. Does that sort of make sense? And so the yes or no question turns out to be, we need it to be yes or no for solving, for more theoretical purposes, but we can modify that to be able to actually find what's the right k for the shortest path. Hamiltonian cycle, the instance in this case would be a graph G, so you're just given some graph, and the question could be, in one case, does G have a Hamiltonian cycle? In the other version, where you're trying to find a shortest Hamiltonian cycle, you could say, given a graph G and a number, does G have a Hamiltonian cycle of length less than or equal to that number k? All right, so rather than looking at these as being trying to find the actual value, trying to minimize something, or in the other case of maximizing something, we're looking at yes or no questions. Okay, so even if the question is not a yes or no, if it's an optimization, we can often turn it into a yes or no kind of question, and that's the ones that we're really looking at, like we did here. Well, I erased it, but like we did here. Does this expression have a way to assign the values? And it's a yes or no kind of situation. All right, all right, so of these decision problems, some of them that we call class P are the ones that have polynomial time solutions. All right, so class P Class P is the set of all decision problems, like the ones that have yes or no answers, which have a polynomial time solution, so that we can answer the question guaranteed in polynomial time, even if the exponent is a big exponent, or even if the hidden away coefficients happen to be big numbers. All of that. That's not relevant in this context. All right. Then there's another class of problems called class NP. Now, NP means non-deterministic polynomial. But we're not going to worry too much about that approach right now. Non-deterministic polynomial means that there's a non-deterministic algorithm that can run in polynomial time. A non-deterministic algorithm means one that is able to make guesses and make the right guesses. Okay, but we're not going to look at it from that approach. We're going to look at it from a different approach, where class NP, that turns out to be equivalent to saying these are the set of problems again, decision problems. This is the set of problems for which a potential solution can be checked in polynomial time. Okay, so we know problems that it's hard to solve the problem, but you can check and answer pretty quickly. We started with problems like that way back I don't know, whenever you learned, before you knew the quadratic formula, how did you solve a quadratic equation? You tried to factor it. But what if it didn't factor or didn't factor in a nice way? Then we cried, right? Well, what would happen? If we couldn't factor it, we might try to do something with graphing where you narrow in on an answer, or we had some other approaches where you tried to come close to an answer. But we couldn't get the exact answer. But if somebody said, well, here's an equation, is this an answer, what would you do? Plug it in, right? Substitute that value in and check to see. If you get whatever you're supposed to get, then, if you're solving a quadratic equation, you try to get 0. If you get 0, then yeah, that's a solution. Where did you get that solution? Don't worry about it, right? Just you got a solution. And so class NP is this set of problems for which you can check a potential solution. If somebody were to say, here, I think this is the answer, you can check that answer and tell. All right, so it's kind of like the potential answer comes from some magical source that's able to answer questions for you, right? You say, give me a guess, and this oracle gives you a guess. This is sometimes called a certificate. So you get a certificate, which is a potential solution. You can check that solution quickly. All right? So class P are the problems that you can solve yourself quickly. Class NP are the ones that says if you had a solution, you could check it quickly. We might not be able to come up with that solution quickly, but we can check it once we have it. All right, so this is the same kind of thing that would happen. Now we know a quadratic formula, so we can solve all the quadratic equations. What if instead of a quadratic, we had a cubic equation? Right, so we had an equation like that. Well, again, we could check an answer quickly. If somebody gave us an answer, we could check to see if we got 0. What if, but could we solve that quickly? Well, it turns out there is a cubic formula as well. There is a formula for solving cubic equations that kind of looks like the quadratic formula, only longer. There's even a formula for solving quartic equations. If we change the biggest exponent to a 4, there's even a formula for solving that, which is even worse. In terms of the extra pieces, because now we're solving for 4 pieces, and there's a lot going on. When I was an undergraduate in our mathematics lab, we had a big poster that was about, it was about half as big as this board, and the quartic formula was all written out, and it was written pretty small, so it took up a lot of space to get those 4 pieces. But there is a quartic formula. All right, so we could solve a quartic. Turns out, though, if you make that a 5, so it's a 5th degree polynomial with all of the pieces, that it can be proved that there is no general formula for quintic or above. And so there's a whole interesting story about the mathematician who came up with that, a mathematician who's by the name of Galois, who's partially responsible for it, and another one by the name of, I've heard it pronounced lots of different ways. But so both of these were in the early 1800s. They both, unfortunately, died rather young. Galois in a duel, and Abel from illness. But anyway, they were able to lay the groundwork to prove that 5th degree and higher, there's no general formula. Involves square roots and adding things and all that kind of stuff that we have for the quartic, or for the quartic and down. So we won't get into that. That's abstract algebra. If anybody happens to be interested in those topics, then do the maths minor or maths major. Anyway, so what happens is sometimes there are certain problems that we just can't solve using certain techniques. So what happens if you're trying to solve those kinds of equations? What would you do if you needed to solve one of those equations? Find a different algorithm, right? Find a different approach. And what does it end up usually being? It usually ends up being some kind of approximation technique. some way of narrowing in on an answer, Newton's method or something, or some variations on that, narrowing in on answers, or using other techniques other than those specific ones. All right, so, but what happens in any of those? If somebody were to give you a 20th degree polynomial and a potential answer, we could check that answer pretty quickly, even if we couldn't come up with the answer on our own. Okay, so class P are the set of problems that we can solve in polynomial time. How do we know for sure that something is in class P? We find an algorithm that's polynomial time. There are some problems that are polynomial time that we don't know that for sure, right? There are some problems that we just haven't found an algorithm yet. So they might be in class P, but we don't know yet. But they're not going to be, I mean, they either are or they aren't. We just may not know on certain problems yet. Class NP, same kind of thing. A problem we might not know how to check an answer. And then later somebody figures out how to check an answer and says, oh yeah, this answer can be checked quickly. But there are other problems that we don't even know how to check the answers quickly. Right? You get a potential answer and it's like, how would I even go about checking to see if that's right? Okay, so there are some things that aren't in these categories. So, but these are both sets of problems. What do you think the relationship between P and NP is? Well, if you can create an answer quickly, wouldn't you be able to check an answer quickly? Check a potential answer? If somebody were to give you a potential answer to a quadratic equation, rather than substituting to check them, what could you do? You could just do it yourself and then compare answers at the end. Right? You could just solve it using the quadratic formula, do it yourself, and check the answer against theirs. So if somebody had a problem that could be checked quickly, but that same problem could also be solved quickly, you could not worry about doing the actual check. You could just solve it and then compare answers at the end. And so it turns out that the class P is a subset of the class NP. Right? If you can check it if you can solve it quickly, then you can check it quickly just by solve it, compare the answers.
Can you solve it more than once and compare them?
No, so like somebody says, here, I think this is the answer to the problem. Do you agree? And instead of using their answer to substitute in or whatever, you just solve it yourself and then just compare their answer to your answer. And if you have the same answer, then what? If you did it correctly and you compare your answers, if they're the same, then yeah, that was the right answer. And if they're not the same, you say, no, your thing that you gave me is not an answer. Right? And the idea of checking an answer, checking a potential solution, isn't to say that, yes, your answer is, it doesn't have to say your answer is correct. It just has to say whether your answer is correct or not. So in this case, you could solve it and then just compare answers and say, nope, your answer is wrong because this is the right answer. Or, yeah, your answer is correct because this is the right answer. So the class P is contained inside the class NP. All right. If you can solve it quickly, then certainly you can check it. You check a potential solution just by solving it and comparing. The bigger question is whether, so we know there are certain problems in here, sorting, Euler tour, a whole bunch of other things we know for sure are in here. Are there things out here? So the bigger question is, if you can check an answer quickly, is it always possible to be able to solve the original problem quickly? And nobody knows the answer to that question. This question has been around for at least 50 years, and no one knows the answer. There are good indications that the answer is no. Some people think that the answer might be yes, but we'll talk a little bit about the details there of what happens here. It turns out that most people who've thought about this problem think that there are problems that are pretty easy to check the answers to, but are really hard to come up with those answers for, right? So that there are problems that do not have polynomial time solutions, but if you had a potential answer, you could still check pretty quickly. So we will look at a little bit of these kinds of problems. All right. So it turns out that if we are a little bit more formal with what these decision problems correspond to, that we can talk about a language and we can talk about the complement of a language. So a language is kind of a formal version of the problem statement. And we want things that will always maybe resolve to be true. And then the complement of that are things that are going to answer that same exact question as false or as no. And so in some situations, we're not going to go in this direction, but we can talk about the problems, and then we can talk about the complement. So we have NP and we have co-NP. So you talk about the problem, and then you talk about, or the language, and you talk about the complement of the language. It turns out that for any problem that you can solve in polynomial time, its corresponding complement can also be solved in polynomial time. So those two are the same thing. But this turns out, again, to be a harder question. If a language can be checked but not necessarily solved in polynomial time, can its complement also? So sometimes you'll see things, if you look up things about NP problems, you'll see this term co-NP sometimes. And I just want you to kind of have an idea right now of what that is talking about. We care right now about a special class of problems in NP. So we have P, we have NP, and we might have things out here. And there's a special set of problems out here. They're called NP-complete problems. Or sometimes we see it written like this, class NPC. Sometimes it's written with a lowercase c. For a long time, I got in the habit of writing it like that. So I'll try to be consistent and write NPC like this. All right, here's the thing about the class of NP-complete problems. First of all of these problems are in the class NP. So it's not all problems that are in that class, but the problems themselves are part of this class. So that means that if you had a potential answer, you could check it quickly. And then all other problems in class NP can be reduced to these problems, to one of these, in polynomial time. So we're going to talk about what it means to be one problem to be reduced to another problem. Okay, so before we get there, the NP-complete problems turn out to be problems that you can turn other problems into. You can take a problem that doesn't look like this, turn it into one of these problems, and then if you can answer it, you can send that answer back. So let's think about what happens in terms of an algebra class. In algebra class, you have equations that you're trying to solve. And so there's algebraic methods over here. But then you also have pictures you could draw of those equations. So there's geometry over here. And so what happens sometimes? Sometimes you have an algebraic problem that you're trying to solve, some equation, and it's difficult. So what do? You draw a picture of it, analyze the picture to come up with a solution, and then send that answer back as a solution to the algebraic problem. Sometimes we have a picture over here we're trying to understand something about, so it's not clear, it doesn't make sense. So instead, we write down an equation, get a solution to the equation, and send that answer back in that direction. All right, so we turn one problem into another, or we reduce one problem to another problem. We also sometimes do this in algebra, just staying on the algebra side. If we have certain, say, quartic equations, we might have quartic equations that can be transformed by changing variables into a quadratic equation. Solve the quadratic equation, do the adjustments, send the answer back to the quartic equation. Right? So if we had something like, well, if we had something like this, what could we do? This equation, we could let u be x squared. And then what does this equation become? It becomes u squared plus u plus 1 equals 0. We know how to solve this with the quadratic equation. And then we take that answer and put it back to here to figure out what x is. All right? So sometimes we do it completely on one side. Sometimes we do the same thing with just two pictures, right? Well, this picture, if you do this, then it can be turned into this other picture, which we can understand better. And we can solve the problem on this easier picture and then bring it back. All right, so this is the kind of idea of what a reduction corresponds to. What do we want to do? We want to reduce problem A to problem B. We need to take this question, right? Here's a yes or no question, and we turn into a question over here, so that a yes answer on this side means a yes answer on that side, and a no answer to this question means a no answer to that question. All right, so the idea is that we take a problem and turn it into a different problem. If we can solve this problem quickly, then what can we do? It means we can solve the other problem relatively quickly. Right? Because what do we have? We want to solve problem A. So we turn it into problem B. That might take some time. Right? There's a polynomial time transformation to turn problem A into problem B. And then we have to solve problem B over here. So polynomial time for the transformation, polynomial time for the solution. But then we have an answer that we can send right back. Yes or no. And so what happens? This problem, let's say we had this problem that could be solved in linear time, but that the transformation took quadratic time. So overall, what do we have? Transform, solve, send answer back. That might be a quadratic time solution, but it's still a polynomial time. All right? So these problems that are NP-complete would be in this class of problems that can be checked quickly, but all the other problems in class NP can be reduced to those problems in polynomial time. So in other words, these problems that are in this class of NP-complete problems these are the hardest problems in class NP. Because what happens? Everything else can be turned into them. And then you can, if you can solve one of those, then you can solve the other problems. Okay, so here's what happens. 1971, Stephen Cook found a problem that fits in this category. Problems that you can turn other problems into. So Cook's theorem says that all decision problems that can be checked quickly prove that all decision problems in class NP can be transformed into a Boolean satisfiability problem in polynomial time. Okay, and a Boolean satisfiability is like the 3 CNF or the 2 CNF situation, except without those restrictions. So it's just ands and ors of a bunch of stuff. All right, and the goal of trying to figure out, does that thing have a solution? So what does that mean? That means you take your decision problem, and by some careful thought, you can turn it into a question about whether or not you can create true values out of this particular Boolean expression. If you could solve this problem, you will either get a yes or a no answer that then goes back to the solution for the original. It's a yes or a no for the original problem. In 1973, a Russian mathematician, computer scientist named Levin, proved the same thing, independently didn't know about Cook's work. So sometimes this is called the Cook-Levin theorem. But what happens is that every problem inside this class of NP problems, by some careful process, can be turned into one of these problems, or this problem in particular. If we knew how to solve this one, then we would know how to solve this one. What do you think happens? Problem is that no one knows how to solve that problem quickly. We know how to brute force our way through that problem. We don't know how to solve it quickly.
You mean the problem of what?
Of this kind of, does this expression have a solution? Does this Boolean expression have a way of assigning true and false values so that you can always make this thing be true? All right, but other problems can be turned into that problem. So what would happen? If we could solve this problem, come up with a polynomial time solution for this problem, what would that do? It would give us a way to solve all these other problems. All right, we turn this problem into that one, solve that one, get our answer back, so we have our solution to the original problem. It is possible. It is possible that these two sets, P and NP, are the same. And it's, well, so for sure some of them are the same, right? Some problems are in both categories. But one possibility is that this is all just one big set. If you can check it, you can solve it. The likelihood is that they're not all one set. The likelihood is that we have something like this.
Is there a difference between Boolean satisfiability and the conjective normal?
Yeah, so the Boolean satisfiability doesn't have that requirement that inside the parentheses are only ors and that there's only ands between. But it turns out that it's pretty easy to replace this with the conjunctive normal form instead. So that's what we're going to do with our example. The conjunctive normal form is easier because you know that inside all your parentheses are only ors, and between parentheses are only ands. So it's easier to organize everything. So this is a more general scenario, but even that specific is still the same, or it's still just as difficult, put it that way. All right, so what do we have? We have the problems that we already know how to solve. We have other problems that right now we don't know how to solve quickly, but we know how to check them quickly. All of these problems can be turned into, right now, into that Boolean satisfiability problem. That's sometimes just called SAT, right? Satisfiability. So if we could solve that problem, then we could figure out how to solve these others. Now, these we don't really care about. These we already know how to solve quickly. Maybe. There are problems inside there that maybe we don't know how to solve quickly, so we could turn it into that, and then that gives us a way to solve that problem quickly if this one had a fast solution.
So there's only one of the instances for...
Well, we needed one to be able to talk about this. All right? So 1971, Cook's theorem says, hey, here's a problem like this. Here's a problem that you can turn other things into. In other words, these decision problems are really just problems in logic. These yes or no problems are really just these kinds of logic problems that involve these Boolean expressions. So in 1972, Karp used this idea and came up with 21 other problems. And proved that they are also inside that NP-complete circle. So now there were 22 problems. And since 1972, there are thousands and thousands of problems that have been discovered to be inside this portion of the decision problem universe. All right, so what happens? Every time a new problem is put into the NP-complete realm, it's a little more confidence maybe that, if any of these problems had a solution, in polynomial time. Somebody would have found one by now. A little more confidence that just being able to check an answer quickly does not mean that you can solve it quickly. But it might just be that nobody's thought of the right approach yet, right? There are thousands of problems out there that are inside this portion of the hardest NP-complete problems. Nobody knows how to solve any of them quickly. Solving one of them quickly would mean what? Every problem inside this circle could be solved quickly. Again, quickly meaning polynomial time. There might still be big exponents. So it might still be like physically intractable. But as far as theoretically, those problems have been solved. Does that make sense? And so this realm of NP-complete problems, again, might not be that much different than other problems that we know how to solve. Right? It turns out that Euler problems are easy. Hamiltonian problems turn out to be in that class of NP-complete problems. Now, there are some other problems that are at least as hard as that, but maybe even more difficult. And so there are things called NP-hard problems, which means that they're at least as hard as these, maybe even more difficult. So there's things outside this as well. But for our purposes, we're just staying inside that realm of things that you can check quickly. You can check answers, but you might not be able to come up with answers. Right? Again, shortest path is over here. Longest simple path is a hard problem. All right. So what's the idea? We want to show that a problem, again, it's a decision problem, is NP-complete. We have a couple of steps that we have to go through. First, let's say I'm going to call this problem A. All right, first, let's show is in our class NP. So we have to show that you can check answers quickly. Now, we want to show that everything else can be transformed into this problem, right? Everything else inside class NP, we want to somehow show that we can turn that into problem A. So how do we show that we can turn other things into problem A? We need to provide a polynomial time reduction of a known hard problem to problem A. In other words, what do we want to do? To show that problem A is hard, we don't want to take problem A and turn it into a hard problem. What would that do? That might take an easy problem and turn it into something more difficult. Right? What do we want to do? We want to take a problem that we know is hard and turn it into problem A. Because what would that mean? That would mean that A is at least as difficult as the hard problem. Does that make sense? So the hard problems that we're talking about are ones that are already in the class NP-complete, class NPC. So what does that mean? Everything can already be turned into them. And so what does that mean? By showing that this problem can be turned into our problem, is that any of these other problems out here can be turned into that one and then turned in to our hard problem. So that all of the problems could be turned into our hard problem. Our new hard problem, right? Problem A.
So a little picture here is kind of as you kind of visualize what number 2 is.
Yeah.
So when you say reduction, for some reason in my head, reduction meant like made it easier, but really was kind of like going from
Just transforming one problem to another problem. Okay. It might not make it easier. It just means that this problem can be worded in this other way, or it can be described in this other way. So yeah, reduction. They probably should have used the word transformation, when they came up with the idea, but because you're transforming one problem to another. But it's just changing the terminology from one problem to another problem's terminology.
So, Cook's theorem, the only NP-complete one I've proven before?
Yes. Yes, Cook's theorem is the only one, because we have to have a starting problem for this to make sense, right? And that's the only one that, other people have proved other problems in the same way just because they can. But yeah, now that we have Cook's theorem, or those other thousands of other NP-complete problems, we don't need to do that in the general sense of how do you transform one thing to another. So yes, Cook's theorem gave us a starting point, a single problem. So then from that point, all you have to do is figure out how to turn that problem into something else. So sometimes there's long chains of things where people have proved NP-completeness of certain problems, and Cook's theorem, the satisfiability, is way off in the past somewhere, right? It's like a chain of things to get you down to this point. But yes, that one can't be proved in this method. All of the others, this is the approach that we take. All right, so does this sort of kind of make sense, the conceptual idea that basically we're trying to say, hey, look, here's our category of hard problems. To get into this category of hard problems, you first of all have to be part of this world. And then anything in here needs to be able to be turned into that problem. So that means, because since everything can be turned into one of these, if your problem, if one of these can be turned into your problem, that pulls then your problem inside the circle as being one of the hard problems. Now, hard does not necessarily mean conceptually difficult. Some of these problems are conceptually difficult. Some of these problems are conceptually super simple. But trying to actually solve them in terms of how do you get the right answer guaranteed every time, that's...
And the vice versa also be true. Not like the opposite also be true.
The problems that are hard to understand might be easy to solve?
Yeah.
Okay. Right? There are lots of problems that are just in class P that are really conceptually difficult, but that are easy to program or easy to find a solution for, or at least relatively easy, right, if you know the pieces. So yes, as far as the polynomial time, the hardness of these problems is computational difficulty, not conceptual difficulty. There are things in all different places that are conceptually easy or conceptually difficult that might be in any of these categories. All right, so what I want to do is actually go through an example of how this process works, of looking at a particular problem and proving that it is actually an NP-complete problem. All right, so let's rewind a little bit and think about the Queen's problem. On the Queen's problem, we were asking, how many queens can we play so that no two attack each other? And we found out that there were 8 queens possible, and that on any bigger size board, we can always put 9, 10, 11, and so on. We didn't go through all the details for the larger boards, but that's a straightforward kind of, even how to place them and so on is straightforward. There's another problem that we could have asked that we didn't ask at the time. I don't think we asked it. What is the least number of queens needed to attack all the squares of the board? So trying to put as few queens as possible out there and attack everything is a similar kind of question.
Disregarding if they were able to attack each other.
Yeah, we don't care if they can attack each other or not. All right, maybe they can attack each other, maybe they can't. All right, so I'm going to stop this for a few minutes and give you a chance to try to solve this problem, and then we'll come back.